Now that we've established how to write multimode states of the electromagnetic field in the occupation number representation, and to relate these to the basic annihilation, creation, and number operators, we should finish this topic by looking more at the properties of these multimode operators. We need to formally understand their commutation relations. We will also find that we can create operators for the electromagnetic field itself, completing our idea of a quantum field theory. We'll start by looking at the commutation relations for operators for different modes. With bosons, it makes no difference to the final state in what order we create particles in a mode. The result of a different order of creation could be viewed as permuting the particles among the single particle states, here the modes. But any permutation of bosons among the single particle states makes no difference to the resulting multi-boson state. Hence, the creation operators commute with one another.
Now we need to look therefore at these commutation relations that we're going to get for operators. Formally then, for creation operators operating on any state, we must have that it doesn't matter what order we create two photons in different modes. Or in the form of a commutation relation, we would say that these two operators for different modes actually commute. Remember, what we're saying is it won't matter if we think about creating a photon in mode J and then one in mode K, or if we think about creating one in mode K and then one in mode J. It will make no difference to the boson state because that order has got no meaning for the boson state of these two bosons we're creating. So, therefore, these operators for different modes commute with one another, and hence they have a commutation relation like this. Similarly, for the annihilation operators, it doesn't matter in what order we destroy particles, so we similarly have a commutation relation for annihilation operators for different modes, J and K. For mixtures of annihilation and creation operators, if we annihilate a boson in one mode and create one in another, it doesn't matter in what order we do that either. Only if we are creating and annihilating in the same mode does it matter what order we do this in. So, with a commutation relation we have previously deduced, we are covering the case where the annihilation and creation are in the same mode. So this is our A dagger less A dagger A equals 1. If these are operators for the same mode, we have this commutation relation. Hence, in general, we can write that for the annihilation and creation operators, they commute unless it's the same mode that we're talking about, and hence we have a Kronecker delta here. So we're just generalizing this relation that we had memorized before and putting in a Kronecker delta. It's now straightforward to construct the full multimode electric and magnetic field operators. We start from our classical definition of the multimode electric field, as we'd written before, as an expansion in classical field modes. We use this relation that we had deduced to get Hamilton's equations, and we substitute the operator P lambda here. We're just proceeding exactly as before, but now formally constructing an operator to represent the multimode field in the quantum mechanical description here. And so for each P, we're substituting the P lambda. We therefore just use our previously deduced operator for the momentum in our expression for the classical electric field to obtain the multimode electric field operator. So this is just a sum of all the electric field operators for each different mode here. So it's a nice simple sum. There's an I out front. There's a sum over all the modes. There is this pair of operators in here and our classical form of the mode and another factor in here. But this is now an operator for the entire field. By a similar argument, starting from the classical expression for a multimode magnetic field, and substituting our operator Q lambda, which is A lambda plus A lambda dagger, we obtain this expression for the multimode magnetic field operator. So this is a quantum mechanical operator representing the magnetic field. And note that it's got A lambda plus the A lambda dagger in here.
So that completes our quantization of the electromagnetic field. If we want to use the electromagnetic field in its full quantum form, we can use these electric and magnetic field operators instead of the previous classical electric and magnetic fields. Evaluating the expectation value of these operators for a given quantum mechanical state of the field will give the expectation value of the corresponding field. We have therefore constructed our first quantum field theory. We'll be able to use this later to work out important quantum effects, such as spontaneous emission, the process of light emission in nearly all everyday light sources, as well as to handle other mechanisms of absorption and stimulated emission. The kind of theory we've constructed, because it's based on the physics of a quite abstract harmonic oscillator, can be simply reconfigured to handle any physical phenomenon that can be written as sets of non-interacting harmonic oscillators. For example, as I mentioned before, any mechanical vibrating mode can also be analysed this way. Such modes occur particularly in molecules and crystalline solids. In a classical view, we can think of systems of atoms as being masses connected by springs. In principle, as a good first approximation, there is a linear spring connecting each mass to each other mass in the system, and the forces from the springs act on a given mass to accelerate it according to Newton's second law. For any finite number n of such masses, we can therefore write down 3n coupled linear differential equations, one for each of the three spatial coordinate directions for each mass. We would then look for solutions of these coupled equations in which every mass in the crystal is oscillating at the same frequency. These would be what we would call the normal modes of this mechanical system. This leads to a matrix equation that can be solved for the eigenvectors with the frequency, or its square, essentially as the eigenvalues. If we change to these eigenvectors as the mathematical basis, we again obtain a set of uncoupled harmonic oscillator equations. The overall amplitude of the mode's displacement from its equilibrium position behaves like the position coordinate of a harmonic oscillator, and a corresponding coordinate based on the time rate of change of the position coordinate and a mass parameter serves as the momentum coordinate. We then rigorously obtain equations for each mode that can be quantized using the harmonic oscillator model we have dealt with. Each mode then has its own creation and annihilation operators, and this analysis leads to a formalism that, when expressed in terms of boson creation and annihilation operators, is essentially identical in concept to our multimode electromagnetic system. Instead of photon modes, we have the normal modes of vibration of the system, and we can think of particles occupying these modes just as we think of photons occupying the photon modes. As I said, in solid-state physics for crystalline materials, the resulting particles are called phonons. We can try to quantize any other linear oscillator system in the same way, and many such quantizations are known, such as plasmons for the collective excitation of modes of charge oscillations in conducting materials, for example, or many other kinds of vibrational modes in molecules. This whole approach, therefore, is a very useful one in the physics of materials and their properties.